Hi, my name is Andrej, and today I will be talking about the improvement of the diagnostic tool for visual representation of the vehicle data. Um, we all know that the automotive industry is constantly improving with the idea of reaching that completely autonomous vehicle. New sensors and ECUs are added, making the communication inside the vehicle much more complex. A big part of this whole process is the testing. Usually the data is saved during this testing, so it can later be thoroughly analyzed and used for different simulations. But another big part of this testing is live analyzation of the data. The data logger is a device used to store this data, and it offers the recording of the data for later analyzation, but also most modern data loggers come with the possibility of the live visual representation of the vehicle signals by offering a separate application that runs on a PC or a tablet device. So after analyzing these types of applications and doing the research, we concluded that these are the most important requirements for these applications. The application for visual representation needs to be simple, informative, scalable, interactive, customizable. There should be an option for the automatic layout, and it should be user-friendly, and obviously all the signals should be synchronized. So we use the typical automotive data logger and the application that comes with it, but also analyze some other applications. Usually this is a sort of the system architecture for these applications in general. On the left, we can see the data logger, which collects data from the vehicle, and also at the same time, a server application is running on the data logger. And on the other side, we have the client application, which runs on a tablet PC or Windows PC. The data logger establishes the communication with the client application. When the communication is established, it sends the configuration. The configuration consists of all the necessary data needed for the visual representation to start, including signals ID, instruments position, size, and so on. After the configuration is sent, the server application starts packing the data logger receives and sending them to the client application. The data is packed in the structure you can see here. So for each value, beside the signal value, also ID and the time difference is sent. These time differences are used to calculate the elapsed time for each signal, meaning that the client application doesn't have its own time mechanism, but the time is calculated as the sum of these time differences. Multiple instances of these structures are packed together into the UDP packets and sent to the client application. So after thoroughly analyzing this application and the other applications being encountered, these are some common issues we found, which are also visible on the application we use to present this solution. When the large amount of data is used, signal lag can occur. Also, after some time passed, signals stop being synchronized. We needed to add new options for starting and stopping the measurement. The button instrument this application offers needed to be improved to support some additional commands for the data logger. We needed to improve the instrument scalability. Also, the labels and signal values were not always visible for every signal. We wanted to make the plotter instrument more configurable by adding the choice where the legend should be placed and choosing the shifting factor of the plotter instrument. Since I don't have too much time, I will just briefly explain all the issues and the solution we proposed, how these issues can be fixed and the whole application can be improved. In embedded systems in general, when handling a large amount of data, there are challenges to do that in real time. So we analyzed the existing mechanism for packing and sending the data and managed to optimize it, improving the ring buffers mechanism and multi-threading mechanism that already existed, which allowed us to work with a larger amount of data avoiding the lag when using so much data. The other problem was signal synchronization. As I already mentioned, UDP communication is used as usual for the streaming, so it is possible that some packets are lost. Since the time for each signal is calculated as the sum of those time differences that are being sent, if some data is lost, the time calculated for each signal can be different. Also, even though the timestamp of the data logger is very precise, even those small errors in nanoseconds can lead to a different calculate time after a long time. So we introduced a mechanism to align the signals. Periodically, we would check which time is the largest and use that time as the time for other signals as well. Also, we would extend the value on the graph so that there are no gaps when the next value arrives. In terms of the customizability of the application, most applications of this type only offer some basic choices when configuring the application, like obviously instrument and signal choices, but also the size and color, font size, and so on. We wanted to show an example of adding an option to change some instrument characteristics live during the measurement. So we added this instrument settings screen, which you can see on the left picture, with the option to change the shift percentage of the plotter live without reconfiguring the application again. Meaning that depending on the traffic and the values we see on the plotter, we can choose the shift percentage without stopping and starting the application again. The application interactivity was improved by adding an additional option to start and stop the measurement. The original application only had an option to start and stop the measurement from the main screen, meaning that the screen where the data is actually visualized would have to leave that screen to start and stop the measurement. So we added an option to enable or disable the start button on the toolbar of the application, which is always visible. The button instrument, which I already mentioned, is used to send some specific comments to the data logger. So we added 3 new options, which are used to switch between 2 modes the data logger offers. There is the logging mode and monitoring mode. Logging mode is the mode where all the data is being stored on the data logger, and the monitoring mode is mode where visualization is possible, but the data is not stored. So these 2 modes can be chosen on the data logger side, meaning that the application had to be reconfigured when the mode is chosen. So by adding these options, we managed to add an option to choose a mode depending again on the values we've seen, and that way save the memory of the data logger, storage memory of the data logger. And also for the starting and stopping the measurement, we added an option to start and stop the measurement using the keyboard on the Windows PC client application. For the user experience, even though all those changes I already mentioned improved the user experience, we also tested all instruments to see which instruments are properly scaled, and for the ones that are not scaled properly, we improved or added scalability. We added an option for the automatic layout, meaning that when the instrument and a signal is chosen, you can set the layout automatically to shorten the configuring of the application. And also we added an option to choose where the legend of the plotter instrument should be placed, under the graph, on the side of the graph, or completely hidden. In terms of the functionality testing, we confirmed that the new options are working. The button instrument is properly changing the modes. The measurement can be started and stopped with the new button. And also we tested the application with the maximum number of signals, which is 150 signals. And a large amount of data was being transferred. And even after a while, there was no problems with synchronization or with the signal lag. In terms of the performances of the application, we tested the application with a different number of signals, using 5,000 samples. And we reached our goal. We set it 200 milliseconds, which is the total time needed for the value to be visualized after arriving on the data logger. So you can see here the times, the 200 milliseconds we set because it consists of 100 milliseconds of a possible UDP delay and another 100 milliseconds for almost unnoticeable delay time. So to conclude, this paper explains the importance of visual diagnostic tools in automotive testing. It talks about the requirements of these type of applications and also explains some common issues and suggests how these issues can be fixed and the application can be improved by presenting the solution on an existing application of this type. Here are the authors, and that's it. Thank you for your attention.
If I understood correctly, you have been able to modify the monitoring and logging application. Am I right?
Well, actually, the monitoring mode on the data logger already existed, if that's your question. We just added an option to choose this mode directly from the application.
Is there any API for all this stuff, so the third-party software could use all the features for the logging and monitoring?
Well, the data logger already offers an API, so another application we created to use to, let's say, lean on the server application, but that's it, I would say. The application only works with that concrete data logger.
Okay, thank you.